All right. Hello, everybody. So before we dive into sorting, we're going to talk a little bit about binary search here. So the idea here is, let's say that we have an array or a vector of data that is already sorted, right? So for example, like the ordered array from assignment 1 is something that's like, okay, it's always sorted like that right here. So we want to find the index of a particular value x in the array, or determine if x doesn't exist, if there are no x's in here. So what's the fastest way we can do this in big O terms here? So we'll sort of start with like the kind of obvious way of doing this, and then we'll kind of progressively sort of see how we can improve it here. So our first attempt is probably just going to be something like this, right? So we've got our array here like that. We have its size, and then we have the x that we're looking for there like that. So we're just going to loop through the array from 0 to size minus 1. If we find an array element that is equal to x, sweet. Where's there an x? It's at index I. And if we get all the way to the end, we return -1 to mean not found there. So pretty straightforward, right? So the best case runtime for this is O of 1, and that is if the very first element of the array is equal to sort of x, like that right there. Now here I'll mention something that I've said a few times elsewhere here. The best case is never, ever, ever when size equals 0. The best and worst cases are always framed in terms of like the size being an unknown. Like size is not something you have control over. You only have control over the stuff in the array, or the x value there like that, right? So the best case should be something that you could apply to an array of size 10 or an array of size 10 million, and it will still give you the best case performance. It's not tied to any particular size here. So don't say that the best case is when the size is 0. Don't say that. Never say that. Don't. If you put that on a test, I will cry into my keyboard. Okay, so that's our best case runtime. If when I is 0, we find x and we return 0, sweet. We're done with like, basically one iteration of the loop there like that. The worst case runtime is if we can't find it, or if we find it sort of like really close to the end, like in the last element or something like that. So then the loop runs n times, and the total runtime is O of n there like that. So best case is O of 1, worst case is O of n there. This is just called a linear search. So it's just start at the beginning, go for it all the way to the end here. Of course, you could start at the end and work backwards from the beginning. But note that we're not using the fact that our sequence is sorted. Like we sort of said, this array here is actually sorted in ascending order here, but nothing about this code uses that. Like this would work perfectly well if the sequence was unsorted here. So let's see if we can't take advantage of the fact that the sequence is sorted to improve this. So let's say that we're looking at a particular array element, right? And it is not equal to x. If it is equal to x, then we're just done. But if it's not equal to x, what can we get from that, right? So if the array element is less than x, then that means x occurs later in the array. Like imagine if x is like, 12, right? So we're somewhere in the middle of the array here, and we find an element like 7, right? So where does x have to be? It has to be somewhere over here in the right half of the array, at some index that is greater than index I there like that. On the other hand, if it's the other way around, right, if the array element is larger than x, then x occurs earlier in the array. Again, like imagine x is 12, and we're looking at our array at some index I, and in this index we find like 21, right? Where does x have to be? It has to be somewhere to the left of that, at some index that is less than I. Since we're looping over the array in the forward direction, right, we're going from left to right here, if the ith element is larger than x, we can just stop right now. Like if I'm looking for x equals 12, right, and I come to a 13 here at position I know that everything over here is going to be greater than or equal to 13. There's not going to be any 12s in the right half of the array. So I can just stop and say, nope, it's not in there like that. If there was a 12, it would have to be over here. But if the loop is still running when I see this 13, that means I didn't see a 12 here. So we can add that into it as a sort of else if in here, where we say, if it's not equal is it greater than? And if it is greater than, that means I don't need to search the rest of the array. I know that it's not going to be found there like that. So that doesn't change the best and worst case big O's, but what it does is it adds one more situation where the best case can occur here. So we currently had a best case where what if the first element of the array is x? This adds another best case where what if the first element of the array is larger than x here? If I'm looking for a 12 and my array starts at index 0 with 27, or excuse me, like 27 or something like that, 7 like that right here, I know that everything in the rest of the array is going to be greater than or equal to 27 too, so there's no point in searching for a 12 in the rest of the array there like that. So my best case is the same, it's O of 1, but it happens more often. There's another situation where it could happen. If you want, you could check against the end of the array, the last element of the array as well there, right? Just to see, is it possible for x to be in this array at all here? So if I have an array, right, that starts with like 20, right, and ends with 37, right? If you're looking for a 12, we can reject that immediately because 12 is less than 20, so it's not going to occur. And if you're looking for a 58, we can reject that immediately because that's larger than 57 there like that. So again, like that doesn't change the best case big O. It's still O of 1, but it adds one more situation where it could happen if the last array element is sort of less than x there like that. So we're just sort of like adding more ways to hit the happy path, to hit the best case there like that. But our worst case is still O of n, right? In the worst case, if you're looking for like a, you know, let's say a 27, right? We're still going to loop through the entire thing here because there could be a 27 anywhere inside of the array there like that. So the optimization that we applied relies on the fact that if we're looking at a sorted sequence, finding an element that is not equal to x tells us more than just that thing, right? In a linear search, we assume the sequence is unsorted. So in that case, like, okay, array I is not equal to x, that doesn't tell me anything about the stuff around that. It just tells me about that particular spot there like that. But if the sequence is sorted, then discovering an array element that is not equal to x tells me something about the rest of the sequence here. If the array element is less than x, then that means x has to occur after it. So that means I can rule out the part of the array up to that point here. Like the x has to occur somewhere over here. It can't occur in that part of the array right there. If the array element is larger than x here, then that means the x has to occur before it. So the x could be somewhere over here, but I know it can't be in that part from position I all the way to the end there like that. So depending on what I pick, I can rule out like huge chunks of the array in one go. I don't have to check each position individually. I may be able to say like, okay, I know that x is not in any of these 20 spots there like that. So we want to maximize the number of array elements that we get to throw out at each step here. So what I should we pick to allow us to sort of like, you know, discard the maximum number of things there like that? And the answer is we pick the middle. Like if I pick I to be n divided by 2, then regardless of whether it's less than or greater than, I'm guaranteed to be able to throw out half of the stuff in the array there and then only search the other half there like that. So that leads to an algorithm that looks something like this here. So we start with I equals size divided by 2. If x is at that position, cool, we're done. We return I like that, right? So that's our sort of like best case is like if the x that we're looking for is exactly in the middle of the array there like that. But if it's not equal, if it is less than, if x is less than array sub I, then we're going to pick the midpoint of the left half here. So we started out looking at the sort of whole array, right? And we grabbed the middle element there like that. So if x is less than that, then we're going to search this half over here by picking the midpoint of that half. That is if x is less than array at the I there like that, right? If x is larger than array sub I, then we're going to let I be the midpoint of the right half. So we're going to zoom in on this part over here and say, all right, what's the midpoint of this section? And then repeat the same process again there like that. So I pick the midpoint of whatever is still left to search and compare x to that particular element. If at any point I've kind of shrunk the amount of array that I have left to search down to nothing, then of course we stop and return -1, right? If there's nothing left to search, then whatever you're looking for, it doesn't exist. Okay, so we're going to use a pair of indexes to keep track of the sort of range of the array that I have left to search here like that. So while I'm sort of searching through the array, like that right here, I could be anywhere from start to end. And unlike the sort of usual way that we use end in C++ here, end is the actual last element here. It's not like, 1 past the end or something like that. So it's the actual index of the last element that the x could sort of possibly be in here. And I just realized I forgot to pass the parameter x to this function. So there should be an int x right in this parameter there, list there like that. Otherwise, we don't know what we're looking for, right? So at the beginning, the thing that you're looking for could be anywhere. So we initialize start to 0 and then end to size -1, meaning that like, okay, the x could be anywhere between position 0 and position size -1. The way that we're going to do this will result in, if the thing you're looking for is not found, end and start will basically cross over each other here. So usually start is less than or equal to end, but if the thing you're looking for is not found, they'll flip, and that will tell us that like, the thing you're looking for doesn't exist here. So our loop repeats as long as start is less than or equal to end, and if that is ever false, we immediately return -1 there. So now we need to find the midpoint between start and end here, which is basically just like the average of the two, right? So it's like, okay, if start is 4 and end is 12, 4 plus 12 is 16, divided by 2, you get 8. That's the midpoint between 4 and 12 there like that. But the wrong way to do this is to just do the literal average of start plus end over 2 there. Mathematically, that's fine, but computationally, it has problems here. So historically, this is how you did it. You used start plus end over 2. You can find hundreds of old textbooks that sort of use this stuff here, right? Books on like algorithms, stuff there like that. The Java standard library contained this code in it there like that. There are even like mathematical proofs, like sort of more mathematically minded computer scientists sat down and proved the correctness of their binary search algorithms using start plus end over 2 here. But it's wrong, and there are situations where it doesn't work and it will make your binary search crash. So why is that? So integers in math, right? Like whole numbers in math, which in math you kind of use this like fancy looking z to represent like all the integers. They live on a number line, and it extends infinitely in both directions. So it extends out to negative infinity in one direction and positive infinity in the other, and 0 is in the middle there like that, right? But integers on a computer, like int or long, right? They don't have an unlimited range. Like an int is a fixed size thing. It takes up, for us, it takes up 4 bytes, four memory addresses there like that. And if you have a fixed size thing, that means it has a limited range. So there is a biggest possible int, which has the name int max, and that is like, 2 billion and change, basically. It's 2 to the 31st power minus 1. And then there is a smallest possible int. That's called int min, and it's negative 2 billion and change. It's negative 2 to the 31st power, there like that, right? So ints on a computer don't live on a number line. They live on a number circle here. Positive is in this direction, and negative is in this direction. So what happens if you try to go too far? What happens if you try to go too far in the positive direction or too far in the negative direction? Well, the way that I've drawn this as like a circle suggests what happens. You loop around to the other side here. So if you do int max plus 1, it takes you over to int min. And if you do int min minus 1, it takes you over to int max. That's called overflow here. You're sort of trying to make a number that is bigger than an int can hold, and it will wrap around to the other side there like that. That's the sort of official thing that will happen there like that, but in C++ it's actually worse. So the compiler is allowed to assume that this never happens. So signed integer overflow is undefined. Like anything could happen here. Like the compiler might make assumptions based on the fact that like, oh, that never happens. It might compile your code in a way that makes like really weird things happen if you do actually overflow. Usually what happens is it does what I've shown here, right? That int max plus 1 is int min, and int min minus 1 is int max. But theoretically, anything could happen if you sort of do this. So if we do this, if we do mid equals start plus end divided by 2, if both start and end are very large, right, if they are bigger than int max over 2, then the sum start plus end will overflow and produce a negative value. And of course, if we do negative value divided by 2, we still get a negative value, which means we'll now be searching at a negative index. And that's going to be invalid. That's probably going to be outside of our array. We're probably going to get like a seg fault or like weird sort of out of range behavior there like that. So that could happen if we were searching like in a really big array, and the thing that we're looking for is close to the end of the array there like that. So we don't want to use just the simple sort of average of start and end. The correct way to do this is to kind of algebraically rearrange it. So the bad thing is start plus end over 2, like that, right? But if we sort of massage it a little bit, we can turn it into this, end minus start over 2 plus start there like that. So start and end, they're always non-negative. They're always greater than or equal to 0, right? They should never be negative because they represent indexes here. And except for like when the loop is done, start is always less than or equal to end here. So if we do start plus end, that is moving us in the positive direction. Like in terms of the circle, start plus end is moving us in the clockwise direction, closer to the int max point, which is where stuff gets weird there like that. So we don't want to do an addition. But if we do end minus start, that is moving us counterclockwise back towards 0. And 0 is fine. Like nothing weird happens sort of near 0 there. So we've basically replaced the addition with a subtraction. If you sort of, algebraically manipulate these two things, you can make them equal to each other. So they're the same in algebra, but computationally, the one that I've sort of boxed here in green, the one on the right, is overflow safe, whereas the simple average is not there like that. So that's the formula that we're going to use to find the midpoint is end minus start over 2 plus start there like that. So we found our midpoint, and now we want to compare x, which again, x should be a parameter to this function there like that, to that midpoint. If x is equal to the midpoint, sweet, we're done. Like we're just sort of finished. So we just return the midpoint as the index at which we found the x there like that. If it's not equal, then we get to do our cool thing, right? So if x is less than the midpoint, so I'm somewhere in the middle of my array here. Here is my midpoint, and x is less than this, right? That means x has to be somewhere on the left. It can't be anywhere on the right there like that. So the way that we do that is by taking the end, which is previously over there, and pulling it over to here, to mid minus 1 there like that. So I say like, hey, I'm not going to search the right half. Instead, the right half is going to get kind of pulled down to be 1 less than the midpoint there like that. On the other hand, if it's greater than, we do the opposite, right? So again, if I have my array and I'm looking at an element in the middle of it here, right? And x is greater than that element, then that means I can rule out not just the midpoint, but everything to the left of it here. So the way that we sort of do that is we take the start and we pull it to mid plus 1, the first element in the right half of that right there. So this is the complete binary search algorithm right here with the sort of loop that keeps running there like that. The mid minus 1 and the mid plus 1s that we do, those are what make it so that start crosses over to basically being end plus 1 if the thing that you're looking for doesn't exist, because we're always doing like a -1 or a +1 there. So the best case is still O of 1 if the thing that you're looking for is sort of in the middle there like that, right? If you wanted to, you could add some checks against the first and the last array elements there to sort of like, add a couple of other best cases here, and those would be, still sort of make it more O of 1 here like that. So that just adds more situations where we get to take the other sort of early exit here. The interesting thing is, what is the worst case runtime here? So we'll do a little bit of sort of algebra here to basically figure out how much are we sort of shrinking the amount of stuff we need to look at if, at each step here like that. So let's let n be the number of things that we have left to search at sort of time I here. So that is just end minus start plus 1 there like that. At the beginning, like the first n is just equal to the size. We have to search the entire thing here. So we want to see how does this change when we go from n sub I to n I plus 1, and we move the midpoint here, right? So if x is less than the midpoint, we're going to move the endpoint to be mid minus 1 here. We're going to do this sort of change here. So the next endpoint, the endpoint at time I plus 1, is going to be the old midpoint minus 1 here. So all I did in this next step here is I plugged in the definition of the midpoint. And here I'm just using the average version, right? Because I'm not worried about like the overflow here. So the midpoint is, algebraically start plus end over 2 here. So it's the old start plus the old end over 2 there like that, right? Like that. Then I'm just taking the definition of n here like this, right? And I'm saying, okay, the n plus 1, the next one here is going to be the end plus 1 of the start plus 1 like that. That's just the sort of definition of n up there like that right there, right? So what I'm trying to do is I'm basically trying to sort of like take this new endpoint and plug it in here. Like that's what the rest of this is doing, is I'm just taking this sort of new endpoint that we have and replacing this with that there like that. So here you can kind of see I've done that here, right? So this is the new endpoint there. This is like the rest of that is just this part up here sort of unchanged. And then I'm just sort of massaging. I cancel the plus 1 and the minus 1 like that right there. And what we end up with is, after we do this, the new number of things that I need to search is equal to the old number of things minus 1 over 2. If you do the other one, right, if you do the x is greater than the midpoint, you get the same result here. So after each iteration, in the worst case, the new number of things left to look at is equal to the original number of things divided by 2 minus about a half here. So we can basically say that at each step, the number of things that I need to look at is half of the previous number of things here. We have a loop that halves its variable each iteration. And we've seen that before. This is going to run in log of n iterations here. Everything inside the loop is O of 1 here. So binary search runs in log of n time there like that, which is better than O of n. So this actually does improve the worst case runtime of our search in a sorted sequence there like that. Right. So let's trace through a couple of these binary searches just to sort of get a feeling for like how they actually work here. So we're going to do a binary search for x equals 5. We're trying to figure out where 5 is in this array. So initially, start and end are just at the end of the array, right? Like I have no idea where 5 is. It might be anywhere between index 0 and index 9. The midpoint, if you do 0 plus 9 over 2, integer math is going to round down. That gives us a midpoint of 4. So we are comparing 5 to 6. 5 is less than 6, so that means I'm going to search left. That means I can rule out not just 6, but everything that comes after it as well there. 5 isn't going to be anywhere in that part of the array. So that part of the array is ruled out, which we do by moving the endpoint down to mid minus 1. So mid previously was 4. End is now going to be 3. So the only place where a 5 could be is in this part of the array right here. So now again, we pick the midpoint. So we do 0 plus 3 over 2. that rounds down to a midpoint of 1, like that. So that's where the sort of midpoint is. Obviously, we have an even number of things. The midpoint is going to have to get rounded, so it rounds like down there like that. So now we're comparing 5 to 2. So 5 is greater than 2, so that means we're going to search right. So we can rule out not just the 2, but also the -1 that comes before it here. So that rules out that section of the array here. Now there's only 2 things that are left to search here. So the midpoint, quote unquote, if you do 2 plus 3 over 2, right, it rounds down to 2. So my midpoint is here. 5 is larger than 2, so that means I'm going to search to the right, so I can rule out that element there. Now end and start are in exactly the same spot, so there better be a 5 here, right? So the midpoint, of course, is the same spot as well. 5 is equal to 5, so that means we found the element at index 3, like that. Now let's do a search for a value that does not exist, like an 8, like in this case. We're searching for 8, and there are no 8s in this array. So we begin by, like, I have no idea where it might be. It could be anywhere between index 0 and index 9. We pick the midpoint. So notice that, like, we pick the same midpoint as we did last time, right? Where the midpoint is depends only on the size of the array there. So for an array of size 10, the midpoint is always going to be at index 4. So we're comparing the 8 to the 6. 8 is larger than 6, so we're going to search right. So I know that there is no 8 here, but also not anywhere over there. So the only place where an 8 could be is in this section over here. So again, we pick the midpoint. 5 plus 9 is 14, divided by 2 means my midpoint is here at index 7. So I'm going to compare the 8 to the 13. Now 8 is less than 13, so that means that 8 is not here, but it's also not over in anywhere to the right of that. So the only where that 8 could be is one of these 2 elements right there. 5 plus 6 is 11. Divide that by 2, that rounds down to 5. So my midpoint, again, quote unquote, is sort of like the left element here like that. 8 is less than 9. So that means I can rule out 9 and also 10, right? And everything to the right of that there like that. So I'm going to do this by moving the end here. So since end is less than start, that terminates the loop, and we sort of return -1 to mean like there was no 8. 8 does not exist here. But notice that, like, if we wanted to put an 8 here, like if an 8 was going to be here, it would be here between indexes 4 and 5 here. So even in the does not exist case here, the end and start indexes give me some useful information. They tell me, like, if you want to insert an 8, insert it before 5, in between 4 and 5 there like that. So it's like still giving me useful information in that case there. So unlike a linear search, right, if you do a binary search, it's not guaranteed to find the first or the last or any particular one there, like if there's duplicates, right? So you can modify binary search so that if you have a range of copies of a thing here. So if our sequence is sorted, all of the x's are of course going to be together. So if you have like x, 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 right, like that right there, you can modify binary search so that it will find the sort of bounds of this sort of range here. So the upper bound would be the sort of first value that happens right before the x's start there, and then the lower bound would be this value right after the x's there like that. So you could kind of find like where the ranges of x's start and stop there like that, right? And those are just like sort of little tweaks to the basic binary search algorithm there like that. You can of course do a binary search recursively like that, right? And then our end and start become parameters to the function, and the recursion is going to modify them. So my base case is exactly what would terminate the loop before. If end is greater than start, that means not found. Okay. We compute our midpoint exactly the same way. If x is equal to the midpoint, we're done. We return the midpoint there like that. If it is less than, we're going to do a recursive binary search in the left half. Otherwise, we do a recursive binary search in the right half. And note that this is linearly recursive and tail recursive. So this has, at least theoretically, exactly the same performance characteristics as the loop-based version there. So anyway, to sum it up, right, binary search allows us to find values in a sorted sequence. Your sequence has to already be sorted. If you throw an unsorted sequence at binary search, it will just give you garbage or whatever like that. In log of n time that there. So our next topic is sorting algorithms. So this will come in handy, right? Like once we have something sorted, we can use a binary search on it to sort of find stuff in it there. And then after sorting algorithms, we'll look at binary search trees, which are sort of like a data structure that encodes what binary search does. So this will kind of like be a useful sort of foundation for what we're going to do next there like that. All right, thanks a lot for your time, everybody, and I'll see you in the next video.